Hi everyone, you're looking at my newest test device here, and this test device is to continue doing experiments with the oriented magnet that was my previous test at 90 degrees. And in this test here, instead of using that 1-inch cube magnet, I'm using two half-inch cube magnets together. So this way I can have actually the poles of the magnets facing the coil. So here we have a south, and here we would have a north. And at the back of them I've got this piece of iron on each one of them, actually transformer laminations, making the path shorted between the two of them, or continuing. They actually, magnets do like to have backing iron. It focuses the flux more to the front. So that's the whole idea there. So we don't need to orient the magnet 90 degrees. We can just, in this configuration, this gives the same result, but you can utilize a smaller magnet because now it's more efficient with the flux at the front. I believe it's giving the same result. All this is just to further test all these ideas and things like that. On top, this is a nice bearing. Actually, I had that in my bucking field test device, the one that exploded. So I'm still using the bearing, and I just super glued all this stuff on. And this is a platter out of a hard drive on top here, where I have my black tape on it and then white tape for the optical sensor switch there that's going to turn on and trigger the drive coil. And that's my heavy gauge wire drive coil, which is 0.3 ohms. And keep in mind, your core should be half the width of your magnets. So we've got 1 inch worth here, and that's about a ½ an inch worth of width of coil. And that is the better configuration. On top, the optical sensor can just be turned. This can be turned on the fly, so you can do advanced or retard timing adjustments, and we're going to be looking at all that. That's my assist coil here that is hooked up to the flyback diode. That's a really fast flyback diode. And I've got I believe it's 17.5 microfarad AC motor run capacitor. I think these are pretty fast as well, or pretty efficient, not too much internal resistance. So here I've got my probe on the voltage here. We'll be able to monitor the voltage of that. And I also have a one of these current probes for the oscilloscope, and I have that set at the 1 volt. It gives you 10 milliamps, I believe. Yeah, 1 volts per 10 milliamps. I don't know. I've never used one of these, but I found one and just put it on. So we can actually see the current happening also in the flyback going to the assist coil. And the assist coil is in a way where I can just remove it, and then we can see the results of what's going to happen when we remove it. And then I can slide it this way to that way, which changes the timing. But I've got a tape there where I've got it tuned now for the test that I'm about to do. So again, these on times here are way too wide. We're going to do more tests and try to find the ideal setting for the pulse width of this. I think we'd get a better results, mostly with the assist coil, to have a smaller pulse width and higher voltage. And all this will be tested. There's my regular switch that I've been using. That's our feed tank, which is 100,000 microfarad, which we have our 0.05 ohm current sensing resistor. These are our voltage at the capacitor, and this is the current that will be running feeding that capacitor, so we can do power calculations. This is the oscilloscope. We're going to have 4 traces happening. That will be our voltage at our coil. This will be the current at our coil, and this will be the voltage coming out of our flyback at the capacitor. and this will be the current probe on that capacitor discharging into the assist coil. So it's not operating right now because the whole device isn't on. Let's give this a spin, and it's going to spin counterclockwise, and we'll connect that up. That is what we are feeding in, our voltage, and it's now going to spin at around 1,500 RPM once it gets up there. So there it is now spinning, and we will take a tach reading on that. So we are definitely at 1,500, more than 1,500 RPM. So 1,035 RPM is where we're at, and operating very smoothly. That is our input, which is actually about 4.5 watts. That is happening right there. That's what that equates to. That is our scope shot. So we see our on time here, and our off time is creating this large flyback spike here, and that is our current during that on time. And then this is our flyback to the capacitor here. So that is the peak right there, and underneath here in green is our current across that drive coil. So I'm going to take a photograph of this right now as I am, as we are seeing this. So that's done, and that's what I'm going to post on the forum. The resolution of the what you can capture on this thing with the USB is like really low, and people are not too impressed with the scope shots, and I probably think it's probably because of that. So we'll just instead take a picture of this and post that. So now for the next test, we're going to remove this coil here, but first we'll just take another reading, make sure where we're at. So we're at 1,520 RPM, and this is our voltage and current. And now I'm going to remove this coil completely out of the equation. So the coil is now removed out of the equation. The current is going up. So we're now over 1 amp feeding the coil. Before we were at around 800 milliamps. And you can hear that our RPM has definitely gone down. So we're at 1,380 RPM and still decreasing. It takes a while before it really levels off and it finds its correct thing. So the assisting coil really helps out a lot in this particular configuration. I think it's pretty well landed now. So it went from pretty well 300 RPM less. Alright, so now what we'll do is we'll, well, maybe I'll give you a scope shot of, I lost my trigger, I think. Okay, so that is now the what the scope shot looks like. And I'm going to take another picture of that so that you can see that on the forum. Okay, so obviously now we've lost RPM, so there's not as many samples in the window. We're down to about 2 samples, and we will put our coil back in position and see the difference. So now I'll bring my hand in, bring the coil in. Let's look at our data here as well before we go. So we have basically 1 amp going in, okay, at 5.2 volts. And I'll keep the camera on this, and you'll see what happens when I bring the assist coil forward. So the assist coil is now in place. And you can hear the RPM increasing. So here I remove the assist coil. You're hearing the RPM slowly going down. And here I bring back the assist coil. And now you're seeing that we are getting increase in RPM because we're getting more samples in the window. Let's take a reading here. So we're at 1,500 RPM where we were previously. And our current is back down to the 800 milliamp range there. So that is that test, and the next thing I'm going to show you now is what happens when we vary the timing. And if I go this way, that way, I'm going to be retarding the timing, and if I go this way, I'm going to be advancing the timing. So right now I'm going to give you a scope shot, a look at the scope shot, and I'm going to retard the timing. So now I'm retarding the timing, and retarding the timing slows the rotor down, but as you see the flyback is greater. And you can tell because the current also to the flyback is up higher. And now I'm going to advance it, and you can really hear the rotor taking off. And now the flyback is getting smaller, and you can see that from the current, and it's dropping down, right? So there it is, operating at a much higher RPM. And what I'll do is I'll try to tune it so that we're using about the same amount of current. So right now we're using about the same amount of current as we were before. But what happens is our RPM is much faster. So we're at 2,100 RPM in this particular way, and there's a little bit of vibration, and that's moving my coil away. Now we advance the timing, so that most likely I would have to advance also my coil here in this direction to get the RPM at the ideal level too. So as you see there, that's about what we're going to get, I guess, about 2,100. And now that is our scope shot, and I'll take another picture of that and so that I can post that. So now I'll just take away the assist coil. So the assist coil has been removed. And our RPM is dropping as well. But not quite as much. And the reason for that is here in the advanced timing position, our flyback is much less. So less energy is going to the flyback capacitor and then to the coil. So that, you know, there are still many things to test here and find out what the ideal settings are. And here I'll just give you another view here of me retarding the timing and what it does. So you can see the differences in the current curve. Here I am retarding, here I am advancing. And you can obviously see the difference in RPM. Advance, retard, advance, retard. So, anyways, I think this is pretty well the middle kind of level here. So in the next video, what I'll be doing is working with pulse width and having smaller pulse width. I'll try to find out the ideal the ideal width and what creates the best for our assistance coil to really kick in. And I believe that should happen when we have smaller pulses and higher voltage, giving us a greater flyback. And we're going to compare the two anyways. So now you see what's going on here, and you saw that with about 4.5 watts we were able to get 1500 RPM, and we can get the same, we can get 2000 RPM for the same input as well. I just demonstrated that as well, and that was by advancing the timing. But then our assist coil is not participating so much. But it doesn't matter. This is like at very small levels, working at 4.5 watts. If it's in a motor, we're probably going to be sending hundreds of watts in that motor. So by that time, the assist coil would be helping quite a bit, I'm quite sure, because the flyback will be much more. Now, the other thing that I found quite interesting is that when I put a load on the device and I have the assist coil in the equation, and we look at the current, and what I'm going to do, I'm going to put my finger on that hard drive platter there, so my finger is on there, and the current doesn't go down as quickly when I have the assist coil in the equation. And the reason for that I've concluded is when you do put a load on the system, like when I put my finger there, the flyback becomes greater. And when the flyback becomes greater, there's more assistance that happens. And that's the interesting scenario that happens here. So I believe a motor that would have this assisting coil would be able to be a little more steady, or keeping the input a little steadier than not having that coil there. So what I'll do now is I'll just remove that coil. You saw me holding my finger there and seeing what happens to the current, and not much change. Okay? And now I'm going to take the coil away, the assist coil, and we'll let this thing fall to its RPM. I'm sorry the video is taking a little long, but I think this is quite important. So let's have a look and see if we're still dropping in RPM here. Okay, that looks stable now. Now, obviously our current has gone up. I'll put my finger and try to keep it exactly the same way. And you can see that right away the current shoots up much faster, and it takes a while to recover. I'm taking the finger off. You can hear it when I put my finger. So I'll put it on again. So it's quite a difference, I find, without the assist coil. And it makes sense because basically the flyback will get stronger but now the assist coil is not part of the equation. And if we look at the scope, I don't know if we can tell what happens. I will put my finger on there again. No, it's too small for the scope to really see something, but we can definitely see it on the current meter there. It's very easy to see. So anyways, that is the new test device, and we'll continue doing more tests, and thanks for your interest. Bye now.